Okay, welcome to the 2.5. So today we're going to discuss continuity, so continuous functions. Let's get started. So first we discuss the learning objectives. So we will discuss definition of continuity, types of discontinuity, properties of continuity, continuity of compositions, so compositions of functions, and what happens if you take the limit of continuous functions, and finally one of the important theorems, the intermediate value theorem, regarding continuous functions. So let's get started. Here's the definition of continuity. So for a function to be continuous at x equal to 3, we need 3 conditions. So first, fc must exist. So it means c must be in the domain, right? The second one is the limit as x goes to c of f of x must exist, right? So limit exists as x goes to c. And finally, this limit must be equal to f of c, right? So the limit of x goes to c of f of x must be equal to f of c. So let me try to illustrate with one with the graph. So what happens is you have a function, right? Some sort of a function. So y is equal to f of x, and here is your c, and we need it to be for this to be continuous. So limit should it should be so first one says that it's defined, right? So this f of c exists, right? It's not something that undefined. And secondly, the limit should exist. So if you approach from left or right, doesn't matter. You need to be approaching to the same point, right? So you need to be approaching to L, right? So this limit should be something like L, some limit exists. And secondly, not only the limit exists, this L must be equal to f of c, right? So L must be equal to f of c. So, for example, I mean, you might have a different scenario where how can you fail the continuity, right? So it might happen that the function exists, right? But f of c could be not here. Maybe it could be somewhere here, right? And here it might be that the limit exists. So this is a situation where limit exists, but so this is discontinuity, right? Or it might be that the limit doesn't exist, right? So this is example of invalidating 3. Okay. So another instance is you might have a situation where the limit simply doesn't exist, right? So the limit doesn't exist. So it might be something like this, right? So let's say that you're looking for c here. So the left limit is approaching somewhere else. The right limit approaching somewhere else. So two different values, right? So the limit this limit doesn't exist, right? Or it simply might be that f of x doesn't. So what could happen is, for example, f of x is equal to 1 over x, and x cannot be 0, right? So if you cannot even ask if the function is continuous at 0. No, it's not continuous because it's not even defined, right? So let us discuss this example. For example, we cannot even ask what's happening on the negative values of x, because the function is not even defined, right? And beyond 4, again, we cannot ask because the function is not defined. But between 0 and 4, we can ask the question at which points the function is continuous, right? So, for example, we can look at this point right here. Right? At this point, I see that the limit, when you approach to this point, whatever it point, like could be 0.5, it exists, right? So it's approaching to the same point, right? 0.5 indeed. And the value of the function here is also fine. However, at 1, the function, so at 1, what happens? If you approach from right, you're approaching to 1, right? However, if you approach from left, you're approaching to 0. So the limit doesn't exist. So this continues, right? So this continues. This continues. So when the function, by the way, when the function is not continuous, we call it discontinuous. So discontinued at x equal to 1 because limit doesn't exist, right? How about at 2? So in here between 1 and 2 it exists, right? This is a constant function. We know that constant functions are, I mean, the limit exists and it's the value equals the limit. So how about 2? So when you approach to 2 from either side, so you are approaching to the same point, which is 1. So the limit, right? So limit of this function as x goes to 2, it's perfectly fine. It exists. It's equal to 1. However, what is f of 2 here? F of 2 is 2, right? Because it's defined right here, so it's 2. So they are not equal. It means it invalidates the third one, right? The limit must be equal to the value at that point. So it's discontinuous. So again, discontinuous. So the same applies at x equal to 2. How about 3, right? If you approach from left, if you approach from right, you are approaching to the same point, 2, and f of 3 is also equal to 2, right? It's right here, so it's perfectly continuous. So continuous, so CTS stands for continuous at 3, etc. Okay, so at 4, okay, we cannot discuss two-sided limit. We can discuss like a left limit, right? So it's left continuity something, and then it's not, because the limit approach to 1, but the function itself at 4 is somewhere else. It's probably like 0.5, so it's also discontinuous. So in the previous example, we discussed the continuity using graphs. Now let's give more a specific function. So let's say that I want to consider the following function f of x. Let's say that 4 minus x squared. So I'm just picking an example from the book. So let's say that we want to investigate the continuity. But first of all, what is the domain? So what is domain? Domain. Well, we know that the inside square root cannot be negative, so 4 minus x squared must be at least 0. So from here, we can see that x must be between -2 and 2. So which means if x is bigger than 2 or less than -2, it's discontinuous because it's not even defined, right? How about inside this interval, right? Well, if you pick, let me just do one example. For example, pick let's x equal to 0. What is so it is defined, right? So first one. So first, f of x is defined at x equal to 0. The secondly, we need to investigate the limit, right? So limit as x goes to 0 of this 4 minus x squared. But what happens if x goes to 0? This x squared goes to 0. So 4 minus x squared goes to 4, right? And then you take the square root of 4. This is approaching to 2, right? It's approaching to 2. So limit exists, right? So limit exists, perfectly fine. And finally, I need to check whether this limit is equal to the function. So what is the value of the function at that point? So what is f of 0? Well, this is just 4 minus 0 squared, which is also 2. So they are equal, right? So equal. So this means, so we conclude that f is CTS, which means continuous at x equal to 0, etc. So in the same manner, you can find out that in fact function is continuous between -2 and the 2, where in the endpoints you consider just one-sided limits. There are different kinds of discontinuity, so let's discuss the 4 types. So the first one is removable discontinuity. So the limit exists, but it's different from the value of the function at that point. So this is an example. You have some function like this. However, so the limit exists. However, the function here either doesn't exist or it's a different point. So if I were to replace this value to whatever the limit is, then it would become a continuity, right? Continuous. So there is kind of a possibility to fix it, right? By just replacing one point. What is jump discontinuity? It's the one-side limit exists but have different values. So this is the situation where you have the limits exists. However, they are different, right? So the left limit approach to different point, the right limit approaching to different point. Infinite discontinuity, so which means at least one of the limits go to infinity. So it might happen again at C. There is kind of what we say a vertical asymptote. So your function might be going from infinity. Here it might be okay, but it's not important. So at least one-sided, one of the limits sort of blows up, goes minus infinity or plus infinity. Oscillating discontinuity, so near limits vary. So basically, it might happen that at this point, your function is oscillating too much. In a sense, it's sort of approaching to different values, more than one value, right? But limit must be unique. So this again invalidates continuity. So we call it discontinuous. So now let us illustrate. So what happens at 0, right? So x around 0. So what happens here? Well, it's perfectly fine. This is continuous, right? So this a is continuous because the limit approaches to 1 and the value at that point is also equal to 1. How about the second one? Well, we see the limit exists, but the function is not defined. But both limits are equal, right? So this is removable, right? So b is discontinuous, but it is removable discontinuity, removable. How about the C? It's also limit exists, but value is different. It's 2, so again it's removable, right? Removable because we could replace this 2 by 1, and then it would fix the continuity. How about the second one? This is jump, right? So there is a jump. So the left limit approaching 0, the right limit approaching to 1, and they are different. So this is a jump discontinuity. So discontinuous, discontinuous, discontinuous. How about this? This is infinite discontinuity, right? So this is infinite discontinuity. Discontinuity because both of them blows, and finally the f is as you can see it's oscillating, right? So it's discontinuity oscillating again, oscillating discontinuity. Well, let's discuss the properties of continuity. So these are very similar to the properties of the limit. In fact, since continuity, definition of continuity involves the limit, all these properties essentially follows from the previous classes where we discussed the limits, the properties of limits. So in particular, if you have two functions, f and g, both of them are continuous at c, then the sum, this new function, is also continuous at c. The difference is also continuous at c. If you multiply the function by constant, it preserves the continuity. If you multiply the two functions, it's also no problem. So f times g is continuous. And if you take the quotients, like rational functions, right, f over g, again, it's continuous as far as g of c is not 0, right, because you cannot divide by 0. And finally, the root, right, if you take the nth root of a function f, as far as this is meaningful, then it's okay. So what do I mean by meaningful? When n is even, the f must be positive, right? Non-negative. Otherwise, it would not exist. Now that we have the properties of continuous functions, we can derive some interesting examples. For example, the fact, we can state the fact that all polynomials are continuous. Polynomials are continuous. So when you say continuous, and if we don't mention the point, it means it's continuous in its domain, right? Whenever it's defined, it's continuous, right? Or sometimes we say a function is continuous on an interval. It means at every point it is continuous. So why the polynomials are continuous? So example, let's say I take p of x to be like 5x squared minus 2x plus 7, right? Well, first of all, I mean, constant functions. Are they continuous? Constant functions. If you take so like a 7, right? F of x, if it's constant, then what happens if you take the limit, right? So if you take a limit of a constant function, oh, see, okay, let's say that let's x go to x0 of f of x. Because it's constant, this is c, so limit exists. And what is f of x0? Because it's constant, it's c. They are equal, it exists, etc. So constant functions are continuous, right? So constant function, so 7 is continuous. How about g of x equal to, let's say, x at any point? Well, if you let x approach to x0, some x naught, what is x? Where does x go? Well, it goes to x0, right? And what is g of x0? Well, because f of g of x is equal to x, g of x0 is x0, they are also equal, so x is also continuous. Now you simply go back that the product of two continuous functions continues. So in particular, it means minus 2 times x is continuous, because 2 is continuous, minus 2 is continuous because it's constant, x is continuous, so product. Similarly, x is continuous means x times x is continuous, right? So which means x squared is continuous, right? And if you multiply by another continuous function, which is 5, so 5 times x squared is also continuous. So now I can take f of x squared minus 2x, which is the difference of two continuous functions that's also continuous, right? And then finally I can add another continuous function, which is 7. Well, this also implies 5x squared minus 2x plus 7 continuous. So with this sort of trick, you can basically prove that any polynomial is continuous. Okay, this is the first fact. Well, similarly, we can also you can also maybe it's more faster because we know the polynomials. The rational functions are continuous. So rational functions are continuous on its domain. So whenever it's defined, rational functions are continuous. Why? Again, you can go back to the properties of the continuous function. So we know that if two functions are continuous, their quotient is continuous. But now we know that polynomials are continuous, right? So, I mean, if you like a proof, so p is continuous, p of x, polynomial is continuous, q of x continuous, right? Let's say that they are polynomials. Then p of x divided by q of x, if you divide two functions, it's continuous if qx is not 0, right? Whenever it's defined. Okay, so that would be the proof of the fact that rational functions are continuous. Another interesting fact is about taking compositions. So if you have two functions where f is continuous at c and g is continuous at f of c, then if you take the g of f, then it becomes continuous at c, right? So that's the theorem 9, or pictorially that's the goal. Okay, so this is again a good important theorem that we can use to show that sort of many complicated looking functions are continuous. So let's illustrate with some examples. Okay, some examples. So let me start with A. So what do we know? Well, x squared minus 2x minus 5, if I denote it by p of x, this is continuous. We know it's continuous everywhere because it's a polynomial, right? It's a polynomial. So it's continuous. Well, the taking square root, if I look at the, let's call it q of x, let's say that this is taking square root. Well, is continuous if x is non-negative, right? Because the limit exists and it equals, etc. So it's easy to see. So then, by the previous theorem, we can safely say that q of p of x, which is now q of p of x, but q is just a square root function, taking square root of p of x, and the p of x is x squared minus 2x minus 5, so that's continuous because of the previous theorem, right? So in a similar manner, you can also prove the others. For example, another interesting fact is that the absolute value is so this is about let's discuss C. Absolute value function is continuous. So what do I mean by it? F of x equal to x is continuous. I mean, if you know the graph, so here is the graph of this function, right? So that's the graph. And by the way, the continuity means in Kazakh uzdiksiz. In Russian, I guess it's called непрерывная функция. So you can see, right, the graph, there is no sort of gaps, right? There is no gaps, so there is no disconnections in some sense. So the graph looks very connected, so it means it's continuous, right? Or if you really want to see it, I mean, when x is negative, what is f of x? F of x is just minus x, right? This is polynomial, it's continuous. If x is positive, this is f of x is just x, right? So it's also continuous because it's polynomial. What happens at 0? So at 0, we see that when you approach from left, it's 0. When you approach from right, it's also 0. And f of x0, f of 0 is also 0, right? So by definition of continuity, we see that it's continuous. So this function, absolute value function, is continuous. Now that you know it, you can show it, right? Like x minus 2, x squared minus 2. So as far as x is not equal to square root of 2, because if x equals square root of 2, the denominator becomes 0, so it cannot be. If x is not square root of 2, so if you pick anything else, then x minus 2 is continuous, x squared minus 2 is continuous, then their quotient is continuous, and then you take the, so you take, for example, let me do it quickly here, somewhere here. So I can take like a g of x to be x minus 2, x squared minus 2, and then my f is here. So this is the absolute value function. Then f of g is continuous, right? By the previous theorem, and this f of g is indeed gives you absolute value of x minus 2, x squared minus 2, etc. With similar thing, you can also show that this sine of x is continuous, cosine of x is continuous, etc. And another property of the continuous functions is by analyzing the graph, essentially, is that if the function is continuous, then the inverse will be continuous. If the inverse exists, then inverse will be continuous, because what is the inverse? At the end of the day, the inverse is nothing but a reflection of the graph along the y equal to x, right? So if the original graph has no interrupts, then when you reflect it, it will not have any interrupts, so it will be continuous. Okay. Limits of continuous functions. Well, this is a theorem. In fact, it's like immediate from definition. This is about taking the composition, but basically what it says is the limit of g of f of x is just g of b. What is b? B is the limit of as x goes to c. So what is really telling you, if you sort of write it out, so what it tells you that when x goes to c, g of f of x, so you can sort of, because what is b? This is g of b, but what is b? B is the, let's write it out, limit as x goes to c of f of x, right? So what it will telling me that when f and g are continuous functions, this limit can go inside when you take the complex, right? So the limit of g of f is g of the limit of f. Okay, so a quick example. Let's say that you want to take a limit as x goes to 1 of the square root of x squared minus sine of x plus 5 or something, right? So you want to take this limit. But we know that square root is continuous whenever it's defined, right? So I hope this is positive, right? When x goes to 1, this is, I hope it's negative. So then it says by this theorem, I can write the limit inside of the square root, right? So I can place it like x goes to 1, x squared, and I can also split the limit, right? Minus the limit as x goes to 1 of sine of x plus limit as x goes to 1 of 5. Right? And then evaluate each limit separately. So limit of x squared is 1, limit of sine of x is minus sine of 1, and limit of 5, because it's a constant, is 5. So this is simply 6 minus sine of 1. So if you know what sine of 1, then we will be able to compute, but this is valid, right? So basically, essentially, because of this, when we know that the functions are continuous, taking a limit is essentially just evaluating the limit at its limit point. So here are the 3 examples. So as I said, I can take the limit inside. So I could write it as cosinus limit as x goes to pi half 2x plus limit x goes to pi half sine of 3 pi over 2 plus x. And then this is simply cosinus. So when x goes to pi half, this 2x goes to pi, right? Plus what happens here, sine function is continuous, so I can place the limit again inside, so this becomes like a sine of, so it's evaluate. So in place of x, you can replace by pi half, so this becomes 3 pi half divided by pi half, which becomes 4 pi half, so this is 2 pi. Right? But what is sine of 2 pi? It's like sine of 0. So this is sine of 0 is 0. So this is cosine of pi. And what is cosine of pi? What is cosine of pi? I think it's -1. Okay, how about here? As I said, this is sine inverse, arc sine, right? This is like arc sine. Arc sine, because the sine is continuous, as I said, the inverse is also continuous, so I can place the limit inside. So take the limit inside, x go to 1, 1 minus x, 1 minus x squared. Okay, now the limit, so this 1 minus x over 1 minus x squared is not continuous because x equal to 1 is not defined. However, we can still compute the limit, right? We can still compute the limit because I'm not asked whether this sine inverse 1 minus x 1 or by 1 minus x squared is continuous. I'm not asked that. I'm just trying to find the limit. So we can still try to find the limits even if it's not continuous, right? So what happens is I could write this 1 minus x squared. So I can write it as 1 minus x here, but here it's 1 minus x 1 plus x, right? Before I evaluate the limit. So then we see that 1 minus x cancel. So you get arc sine of limit as x goes to 1, 1 over x plus 1. 1 plus. What is, as x goes to 1, x plus 1 goes to 2, so this is 1 over 2. So this is arc sine 1 over 2. So it means at what, for which theta, sine of theta is 1/2. So that's the question, right? So this is 30 degree, I guess. So it's pi over 6. And finally, let's quickly do this. So this is simply letting x goes to 0. So this is square root of 2. And here it's e to the tangent 0, but tangent 0 is 0. So this is, and the square root of 2 e to the 0. So this is square root of 2 because e to 0 is equal to 1. Okay? Okay, the last topic that we cover in this section is intermediate value theorem. Shortly, we call it IVT. This is a very important theorem, in fact, in the theory of continuous functions. So what it says is the following. If f is a continuous function on a closed interval, so AB, and if y0 is any value between f of a and f of b, so y0 is right here, right? So my f of b is here, between, right? So my f of b is here, my f of a is here, so y0 lies between these two. Then it says there exists some c in this domain, right? I'm assuming that I'm defining right here, so I can find a c in here that assumes this y0. So f of c is equal to y0. So its intermediate value exists, right? So if I pick another one, like here, then the theorem tells you there is some point here that whose value will be equal to this one. Okay, so this is the intermediate value theorem. Let's consider one example to illustrate how we can apply intermediate value theorem. So it's about proving. So we want to prove that this x cubed minus x minus 1 equal to 0. So there is some x, there is a root, right, for this equation. This is cubic equation, and I mean, from high school we know that we can find the roots of quadratic equations, but for cubic equations it's a bit challenge. So, but we are not trying to find the root, we want to show that it exists, right? So existence. So okay, let's do it. So let's take f of x to be x cubed minus x minus, and so we want to show that the root exists between 1 and 2. So let's see what is f of 1. because f of 1 is 1 cubed minus 1 minus 1, so this is negative 1. And what happens in the other extreme? So f of 2, this is 2 cubed minus 2 minus 1, so this is 8 minus 3, this is 5. So I don't want to sort of, I don't want to attempt to sketch the x cubed minus x minus 1. However, we can sort of plot these points, right? So here is my 1, here is the 2, let's say, and at 1 I have negative value, right? So at 1 I'm negative value, so it's somewhere here. At 2 it is 5, right? So somewhere above, let's say that this is 5, right here. And then I need to sketch that. I know that this is continuous function, right? This is continuous function. So I need to sketch a graph without sort of pulling my hand, right? So there shouldn't be any interruptions. So you need to sketch some sort of a graph, right? Well, when you sketch, because you're passing from negative value to positive value, right? So I need to sort of go from -1 to 5. I have to intersect this x-axis at some point, right? So this point is going to 0. So this is intermediate value theorem. So what we say is, so here is how you write. Here is if you like a proof. So since 0, so I'm looking for 0, right? Since 0 is between -1 and 5, by intermediate value theorem, there is a c or x, whatever, between 1 and 2, right? Between 1 and 2, because we evaluated at 1 and 2, such that this f of c is equal to 0. And what is f of c? So this is my function, so this is like c cubed minus c minus 1 is equal to 0. So it means c is the root, right? So c is the root. Okay, so I'll stop here.